Now we come to the representation. Suppose I have a vector A belonging to the uh, first vector space, and I have B, an element of the second vector space. Uh, so A tensor B is an element of the tensor product vector space, and I can represent it by another column vector. For example, let's say I have two vectors, and that would be represented by a column vector with a dimension of 4. This is going to be an n into m dimensional column vector. Similarly, if I have one tensor 0, 1 belongs to V, this vector belongs to W, so I'll have and that will be given by, one can also define an inner product on the tensor product vector space, and that's rather easy. I have an inner product of two vectors belonging to V tensor W vector space. The inner product is just the product of these two complex numbers, where A and C both belong to V, and B and D both belong to W. So now, if I have given two linear operators, A is an element of the linear vector space V, it's an operator, and B is an operator in the linear vector space W. Their tensor product A tensor B is going to be an operator in V tensor W, and as we know, the set of operators form another vector space, and the action of A tensor B, the operator on a given vector in V tensor W, is specified by simply A tensor B, where I'm using A analogously and B in the bracket notation. And in general, any operator of the form a linear combination of operators AI and Bj, where AI is an operator on the vector space V and Bj is an operator on the vector space W. This is also a linear operator. So it was essential for us to build this thing up in order to understand entanglement, because entanglement is a very essential and a fundamental feature of quantum mechanics. when we have quantum states on composite vector spaces. So next we go to the basics of entanglement.